Now today's lesson is about lattice energy, right? So lattice energy, what is lattice energy? When oppositely charged ion attract each other, right? But we have to write down a proper definition for lattice energy, right? So here lattice energy, what we mean by lattice energy is enthalpy change when one mole of ionic compound is formed from its gaseous ions, right? Again, if you don't like to memorize, think about a reaction, right? Think about something like this. Now, let's think about lattice energy of sodium chloride. So you make 1 mole of sodium chloride, right? So you make 1 mole of sodium chloride. So sodium chloride should be in solid state, but from gaseous sign you are making, not from the aqueous sign. You are making it from the gaseous sign. So enthalpy change when 1 mole of ionic compound form from its ions, gaseous ions. Now let's think about another one, magnesium chloride, lattice energy of magnesium chloride. So lattice energy of magnesium chloride, it's MgCl2. So it should be in solid state. You make MgCl2 from Mg2 plus gaseous ions. But how many chloride ions you need? You need 2. Now this side can be any number of moles, but remember this should be always 1 mole. Ionic solid should be always 1 mole. So shall we quickly write down these 2 examples? So lattice energy we use usually delta H theta Le. Delta H Le is lattice energy. Standard lattice energy is theta, delta H theta. So it is the enthalpy change when 1 mole of a ionic solid formed from its gaseous ions. Gaseous ions always should be from gaseous ions. Right. So I'm going to do the lesson a bit faster. Therefore, you also need to write down faster. I'm going to experiment something today. So when you do it faster, you won't remember that you're hungry. Anyway, we have to get ready for that. One day we might live without food. Right, okay. Can I erase this? Right, now let's write down the definition for lattice energy. Is this? Right. It is enthalpy change when 1 mole of ionic solid one mole of ionic solid is formed from its gaseous ions. From its gaseous ions. Right. So that is the enthalpy change, lattice energy. Right. Now lattice energy. Think about lattice energy. How whether it's exothermic or endothermic. What do you all think? Lattice energy, is it exothermic or endothermic? Exo, because bond forming is always exothermic, right? So lattice energy is always negative because it's bond formation, right? You can write down that. Lattice energy is always exothermic. Always exothermic due to every standard lattice energy. Here we just wrote down lattice energy. Lattice energy is always exothermic due to bond formation. So bond making is always exothermic. Right. The other thing is, if a strong lattice is formed, if a strong lattice is formed, always strong electrostatic attractions are formed. What do you think? More energy is released or less amount of energy is released? More, right? So if lattice energy is more exothermic, that lattice is strong. Do you get it? So if I say a certain lattice has lattice energy which is highly negative, which means that lattice is very strong, because when you make strong bonds, you release more energy, right? So we can write down that if lattice energy is more negative, or more exothermic, the strength of the lattice is greater. We can write down in brackets. If a lattice is strong, what do you think about the melting point of that pi, right? Therefore, high melting point. Right, so many things now. So if a strong lattice is formed, always it's more exothermic. Delta H will be a highly negative value, right? That means it's strong. And if the lattice is strong, melting point of that lattice is really high, right? So shall we do a few examples now? So let's go to the next part. Now they have given us some details. Lattice energy always depends on charge and the ionic radius. You remember charge density? Charge density, we discussed charge density. Always the charge of an ion should be high. Ionic radius should be what? Smaller, right? So if you put if you put a certain charge in a small area, here the charge is highly dense. So the negative ion can feel this charge really well. Always the size of the ion should be very small. The charge should be very high. So now to have greater lattice energy or more exothermic lattice energy, you need to have a greater charge and smaller ionic radius, right? Now we are going to compare lattice energy of the following compounds. So we have NaCl, NaBr, NaI, right? So all of them contain sodium ion. So therefore, no point of thinking about sodium ion. So we are thinking about the other ion, halide, Cl minus, Br minus, NaI. So I'm going to give you a chance which lattice energy is more exothermic or more strong. NaCl. Why? Because chloride ion is small. Now here we have two things to discuss: charge and ionic radius always. But charge of each ion is -1, -1. So we are thinking of the size now. Chloride ions are smaller, therefore the lattice is more stronger, right? So we can write down the ionic radius of chloride ion. Smaller. Therefore, electrostatic attractions are strong. Are strong in NaCl. Hence, the lattice energy is more exothermic. So if I say more exothermic, that means high melting point, right? So always when you have strong electrostatic attraction, then the lattice energy is always high. So to do that, we need a small ion with or greater charge. So here the charge is same, but the size is smaller in Cl minus, right? So I'm going to give you a chance to think about the other one. Now, when it comes to ionic lattice, so when you're thinking about the electrostatic attraction, this is the thing. There may be two chloride ions. It doesn't matter. We think of the attraction now in a lattice, let's say calcium ion per 1 calcium, we need 2 chloride ions. But we are thinking of the charge between 1 calcium and 1 chloride ion, right? So with that, can you decide which one? CaCl, because calcium has greater charge, right? So always charge is first. We think about the charge first, then we can think of the size. But here, charge is different. Therefore, calcium chloride is more exothermic, right? So let's write down. The charge of calcium is calcium 2 plus is greater. Greater than Na plus. Therefore, the electrostatic attractions are strong in calcium chloride. Hence, lattice energy is more exothermic. Lattice energy is more exothermic. Right. Now you're going to do this. Right. Now you're going to do third one and the fourth one. I'm going to come and check your answer. Right. So always what you need to do is simply you select which one has the highest or strongest lattice energy or lattice or the one with more negative lattice energy. Right. Then explain your answer. Right. So we have 3 and 4 to complete. Periodic table. Oh. And I think of the periodic table from the beginning. Your teachers ask you to study up to 20th one. Which is the 20th one? During grade 8? No? Right, done? Now you ask, what is it now? The exam is over. By the time you find that calcium is below magnesium. Now, periodicity, sodium, magnesium, aluminium, phosphorus, silicon, phosphorus, sulfur. So, calcium is definitely below magnesium. That any baby knows. We can ask from anyone on the road, they will answer that. I don't know why these students, they don't know where calcium is and magnesium. Now in the new syllabus, they don't provide the data booklet. Yeah. They give, no, they give periodic table. They give the data in the question. No, they are lucky because you don't have to look for the data. It's there in the question. If you need at ionic radius, it's there in the question. That's easy. And the MCQ don't have that only A first one. Only A is correct. That only one is correct. They don't have that. It's just normal MCQ. Really? I didn't know that, but don't be jealous here. Finish your A-levels first and finish this question. So unfair. Right. Anyone from online that will finish the question, you can WhatsApp. Physical chemistry is where you can score a lot because the answer is certain. Like organic, there's a lot to think. What? Oxygen? You won't know whether oxygen is below sulfur. Like you guys come to my grade 9 class. I think you guys belong there, not in my A2 class. Some students who have joined physically don't know where oxygen sulfur is placed in the periodic. Right, done. First one. What's the answer? What's the answer? Huh? Yes. Yes. Right. In the question number 3, the ionic radius of magnesium is smaller than calcium 2 plus Mg. The ionic radius of Mg2 plus is smaller than calcium 2 plus because magnesium is above calcium, right? Therefore, so the ionic radius of magnesium is magnesium 2 plus is smaller than calcium 2 plus. Therefore, the electrostatic attractions are strong in MgCl2. That student can jump from this field. Right. Therefore, the electrostatic attractions are stronger in MgCl2. Hence, the lattice energy is more exothermic. Next one. Next one. We have three. We have three ionic lattices. We have NaCl. We have calcium oxide. We have calcium sulfur. Now, when you see NaCl, you remove it completely because in that sodium is +1, Cl is -1. So negative, like the charge is +1 and -1. But in the other two, calcium is 2 plus and 2 minus oxygen, right? So in that case, sodium chloride is completely out because the charge is less. Now we are thinking of calcium 2 plus, calcium oxide and calcium sulfide. Now we have a competition because anyway, I'm not thinking about calcium ion because it's common, right? But the competition is between the oxide ion, which is 2 minus, sulfide ion, which is 2 minus. Now, where is, okay, sulfur is below oxygen. Therefore, size of sulfide ion is larger. Oxide ion is smaller. So that's what we need, right? We always want the ion to be smaller. Or in other words, we can say, whenever the ion is smaller, the charge density is high. Do you get it? Like, do you feel it? Like, charge is highly dense means small ion. If it is larger, charge is like diluted over a large area, so the incoming particle can't feel the charge. You have to always like think like that, right? So we need small ions so that the charge density is very high, right? So in your answer, you should say, right? So you should say that the oxide ion, sorry, ionic radius of O2 minus is smaller than S2 minus. S2 minus, right? Therefore, the electrostatic attractions in what? In what? Calcium oxide, electrostatic attractions in calcium oxide is stronger, are stronger. Therefore, the electrostatic attractions in calcium oxide are stronger. Hence, lattice energy is more. Hence, the lattice energy is more exothermic. Now we have a big problem, okay? We have calcium sulfide, we have calcium chloride, we have sodium sulfide. Which one we are going with? calcium sulfide, because in calcium sulfide, calcium is 2 plus and sulfide is 2 minus, right? So the charges are greater, right? So greater, like strong electrostatic attractions in calcium sulfide, because calcium has 2 plus charge and sulfide is 2 minus, right? So we can write down like this, right? So calcium sulfide contains calcium 2 plus and S2 minus. Now S2 minus is 2 minus, huh? Not like nitrogen N2. Some students are sleeping and they write whatever they think, right? So it's calcium sulfide contains calcium 2 plus and sulfide ion, S2 minus. Therefore, the electrostatic attractions are very strong. Hence, the lattice energy is more exothermic. Hence, the lattice energy is more exothermic. Now we have a challenge in next one. Don't write that. Don't write. I said now we have a challenge means it's not written in the answer. Okay. Now, what if we get this kind of a compound? Right? See, challenge one. Okay. Calcium chloride, Na2S. Now they actually have similar lattice energy. You understand why? Yeah. Now see, this is plus 2 and this is plus 1. This is minus 1 and this is minus 2. We get it? Here the cation wins, here the anion wins. Right? So therefore both lattice energies are almost equal. Now we're gonna do a small calculation, right? So what we're gonna do is we're gonna calculate charge density of each ion. Let's say we take calcium chloride. So we're gonna calculate charge density of calcium 2 plus and the charge density of chloride ion. And we're gonna calculate charge density of Na2, Na plus and S2 minus charge density. So charge density is charge divided by the ionic radius, right? Charge divided by the ionic radius. Now charge is plus 2, but how much is the ionic radius? How do we find? From data booklet. You all have the data booklet with you? Very good. Coming for the chemistry class without the data booklet is like going into war without a gun, right? Discuss the paper. Baba? Right. I will share the data booklet with those who have joined online. Right. So in data booklet, in page number 10, as I remember, we have the ionic radius of most of the ions. So we'll go to data booklet because I'm writing. No. Right. Now the ionic, I'll tell you the ionic radius of calcium 2 plus. Quickly write down. Calcium 2 plus is 0.099. 0.099. Right. Then you can write down for the ionic radius of Na plus is 0.095. Ionic radius of chloride ion is 0.18. 181, sorry, 181. Ionic radius of sulfide ion is 0.184. 0.184. Right, let's calculate charge densities of each ion. Done? No, just calculate. Right. Okay. Charge density of calcium 2 plus is 20.2. 20.2. The charge density of sodium is 10.5. The charge density of chloride ion is it minus 5.5. Then this is minus. See now the charge density, it's like this. Now these are two teams, right? So two teams, 10.8. 10.8, right? So let's think like this. Right. The charge density of calcium is almost twice the value of Na plus. The charge density of sulfide is almost twice the value of Cl minus. Do you think the powerful, like, can you compare the two teams now? Here we have a powerful fellow. Here we have the anion, which is powerful. So then the lattice energies are same. Do you get it? The logic, right? Here we have a powerful one that has like twice the value of this. Here the anion has the twice the value of this. So the lattice energies are almost similar, right? So we can write down like this. The charge density of calcium 2 plus. The charge density of calcium 2 plus is twice the value of Na plus. Twice the value of Na plus. Then in another point we can write down the charge density of sulfide ion, S2 minus, sulfide ion is twice the value of Cl minus. It's like almost twice, right? Cl minus. Therefore, electrostatic attractions, electrostatic attractions in calcium chloride and sodium sulfide, CaCl2, Na2S, electrostatic attraction in calcium chloride and sodium sulfide are similar. Get it? So sometimes they can be similar, right? So the question will be like this. Examiner will ask, explain why calcium chloride and sodium sulfide has same, similar, or almost equal lattice energy. So the examiner has given us the answer. So then we have to say the charge densities are like this. And also in the question, they will say use data booklet. So you have to write down the values. And write down the values. Always when they ask you to use the data booklet, you have to write down the values. They give 1 mark for that. Ready? Right. So now we'll go to the next page. Right. Now, today we're going to learn the most interesting one. This is going to be really interesting. Okay. But you need to learn properly. Right. Here, after today, everything is like more logical compared to ACE level. Like we had, like, remember inorganic colors, you have to remember. Reactions, you have to remember. Here, now in A2, less things like that. Okay. Physical chemistry, especially, there's another me. Multi-universe. Multi-universe. Yeah, fine. More than that. If you open your eyes, huh? Right, let's go to the next part where we're going to discuss. Right. Born-Haber cycle. Now this fellow, right? Born and Haber, two fellows. Right? Right, so they were friends. So now they were like, okay, so let's come up with a method, like, Hess cycle. Let's come up with a method to find out lattice energy, right? Now we already have this equation where, lattice energy is where, gaseous ions combine to form 1 mole of ionic lattice, right? Okay. Now 1 mole of ionic lattice is formed from its gaseous ions. Right, some technical problems. Hmm? Yeah, something's wrong. But anyway, I don't need the stupid this projector for this. Yeah, no, I actually don't need. Right, now this is the thing, right? So we know like how ionic lattice is formed from its gaseous ions, right? Now, if you think about sodium chloride, NaCl solid formed from its gaseous ions, 1 mole of ionic solid formed from the gaseous ions, Na plus and Cl minus. Now they wanted to, combine. So this is lattice energy, right? Then they wanted to combine formation enthalpy to find out lattice energy, right? So formation enthalpy definition, do you all remember? Formation enthalpy is when 1 mole of a compound formed from its elements. Elements. Formation enthalpy is that. So what are the elements for sodium? Na solid. Sodium in nature you find as a metal. Sodium solid. Chlorine in nature a gas. Cl2 gas. Right. So but we need to put half in front of chlorine. Otherwise, you have only 1 chlorine there. So you can't put 2 there because it should be 1 mole of ionic solid. Right. Then they realize, okay, so this we can call formation enthalpy. But what is this? This has so many steps. To make a gaseous ion, you have to convert sodium solid first of all into gaseous atoms. Then you can remove the electron to form gaseous ion. So think about chlorine molecule. You have to break the chlorine molecule and make atoms, right? Then you can put the electron to make it -1. So a lot of process involved. Then they realize we can't solve this using Hess cycle. So then Haber and Born and Haber got together. They made a method. Born-Haber cycle is what we're going to learn today. Very simple. But before that, we have to know few examples. I mean the definitions, right? So let's mark everything like this in your Hess cycle. Delta. This is lattice energy. This is formation enthalpy. This is a question mark. What? Mystery. So today, biggest mystery of the year. My birthday is the biggest mystery. It's in this month. What? Then minus 1 mark for each mock exam. Right, minus 10 marks. Okay, now do you remember first ionization energy? Right? First ionization energy. Now it's like, do you remember the definition? Nafa remembers because she is doing his October, November exam, right? Right, now let's, okay, everyone focus here. First ionization energy. First ionization energy, IE. Right? So what I do is I remember a reaction, then I can come up with the mechanism. I mean the definition, right? So first ionization energy is you take a gaseous atom, you remove one electron, 1 mole of electron, to form unipositive gaseous ion. Get it? Now second ionization energy is, what is second ionization? Now some students think you take a gaseous atom, remove 2 electrons, that is second. No, after first ionization energy, you take this one now, remove an electron from that. If you know mathematics, if you remove another electron, this will become Na2 plus. Naturally, it's hard to do this, but you can do it forcefully, right? So this is first ionization, this is second ionization. Now see, right, once you know the reaction, you can come up with the definition. So this is first ionization energy. It is the energy required to remove 1 mole of an electron from 1 mole of gaseous atom to form 1 mole of unipositive gaseous ion. We get it? It is the energy required to remove 1 mole of electron from 1 mole of gaseous atom to form 1 mole of unipositive gaseous ion. Right. So let's write down on the first ionization energy. First, we'll write down the reaction, then we'll write down the definition. It's a mistake. Was never born. They don't know. That was on the wrong day. Right. Shall I write the definition then? Under first. Right. Under first ionization energy. Right. Write down. It is the energy required to first ionization. Okay. It is the energy required to remove 1 mole of an electron. It is the energy required to remove 1 mole of an electron from 1 mole of gaseous atom one mole of gaseous atom to form 1 mole of unipositive. Unipositive means plus 1. Unipositive gaseous ion. Unipositive gaseous ion. Right. Now we know the second ionization energy reaction, right? So you remove 1 mole of electron from the unipositive gaseous ion. So it is the energy required to remove 1 mole of electron from unipositive gaseous ion to form dipositive gaseous ion. Okay? This is known as dipositive, this is unipositive. Can you write down the definition then? Right? Done? Right. So did you write down that it is the energy required to remove 1 mole of an electron from 1 mole of unipositive gaseous ion? It is energy required to remove 1 mole of an electron from 1 mole of unipositive gaseous ion to form 1 mole of what? Dipositive gaseous ion. This obviously not under standard conditions because you have to make gaseous atoms and stabilize it. Now the next one is opposite of ionization is known as electron affinity, right? So it is not removing, it's gaining 1 mole of electron, right? Gaining 1 mole of electron, right? So let's go to electron affinity, first one, electron affinity. Right, electron affinity 1. First electron affinity. Now this is what happens when you when it's electron affinity. So it is the energy, right? It is the enthalpy change when 1 mole of gaseous atom gain 1 mole of electron to form 1 mole of uninegative gaseous ion. Enthalpy change when 1 mole of gaseous atom gain 1 mole of electron to form 1 mole of what? Uninegative gaseous ion. Get it? Right. So let's write down first one. This is can. Can. Yeah, write down the reaction. Electron affinity 1. First electron affinity. Second electron affinity for oxygen. Now you start with, like, if it is second electron affinity, you start with this, O minus. Right. Can anyone give me the definition for this? This is the reaction, right? So you gain 1 electron, you become -2 now. Gaseous ion. Gaseous is important, okay? Yes. Right. So shall we write down the definition for first ionization? I mean, first electron affinity. Right. So write down, it is the enthalpy change when. It is the enthalpy change when. Yeah, energy change or it is anyway difference. Yeah. It is the enthalpy change when 1 mole of a gaseous atom. 1 mole of a gaseous atom gain 1 mole of an electron. Gain 1 mole of electron to form 1 mole of uninegative gaseous ion. It is enthalpy change when 1 mole of a gaseous atom gain 1 mole of electron to form uninegative gaseous ion. Now you can write down the electron affinity 2, second electron affinity reaction, and then you can write down a definition for that. We call this uninegative gaseous ion. The other one is di-negative gaseous ion. Good question. Right. Now we are in what? We're in 8-2, right? So now brain has matured. We don't give stupid answers like we gave in 8th level. Remember some students, when I asked why nitrogen compare the boiling point of nitrogen and oxygen. They write nitrogen has a triple bond, so higher boiling point. Oxygen has higher boiling point than nitrogen. You're not breaking double bonds or triple bonds in boiling or melting, you're breaking van der Waals. Oxygen has more electrons, strong van der Waals. That's it, right? So like those answers, we are not giving answers in A2 because now if you give that kind of answer, you'll be asked to say for like 30 minutes after the class to go through rehabilitation. Now, my question is this. Think about ionization process and tell me whether ionization enthalpies, are they positive, are they negative, or can they be positive or negative? Ionization energies are always positive, are always negative, or can they be positive or they can be negative? Positive. Right. What do you do in ionization? You take that electron out. So you need to anyway put some energy. So the reaction requires some energy always. So ionization enthalpies are always positive. So we have this ionization 1 and 2. Put a bracket to that. Always positive. That's for ionization 1 and ionization 2. They're always positive because you have to put a lot of effort to remove that electron, right? So that means it's endothermic always. Now, when it comes to electron affinity 1 and 2, there's a slight difference, right? Yes, electron affinity 1 is negative. 1 is negative. So oxygen likes to take electrons. But as you asked, next electron is taken by a negative ion. So a little bit of effort has to be put, positive. So oxygen's electron affinity 2 is always positive. Negative, second one will be positive because of the negative charge that is already there. Third one, right? Third one is going to be positive definitely. But the thing is, we don't use that in reality. Like it's not a feasible ion for oxygen. Like in because our plan is to find out lattice energies, you will never find O3 minus. So you will never find Cl2 minus, but you will find O2 minus definitely. Right? So in that case, we should know the second second electron affinity of oxygen is positive due to repulsion. Yeah, that is that. In N3 minus. Yes. You get it? Because we are going to pair this electron, there will be repulsion. So we need to put some effort. That's why this is electron affinity 2 is positive due to repulsion. Right now, these things you don't have to memorize. Automatically, you'll remember because I'm going to give billions of Bornheimer graphs today, cycles, for you to practice, right? But as a teacher, I will demonstrate one, and then throughout today, you'll be doing no breaks today. Yeah, because I had to take some time to fix everything. Right, shall we go to page number? Shall we go to page number 4? Yeah, we both discussed about that. Right. Let's go to page number page number 6. I like sodium oxide. I gave that in the mock exam also. Right, let's go to, so I'm going to do one and then you're going to follow my method. Don't write anything. I will give you time to copy down. No. No breaks today. Yeah. Because we never gave breaks for A2 class. I feel like if I give breaks, I won't have enough time to cover it. But we have to take that advantage and, yeah, I'm going to give a break, definitely. Around 5. Right, now listen to this. We are going to find out lattice energy of sodium oxide. Sodium oxide is the lattice, right? And they will provide you some data, right? They will provide you some data. Look at the data they have provided. Atomization of sodium. What's atomization of sodium? Yeah. Ah, no. No. Atomization, not ionization. Atomization. Think about this, okay? Atomization is you make gaseous atoms from the element. It can be Na solid then. You make sodium gas. If it is chlorine, Cl2, becoming Cl atom. So one Cl atom, which means half Cl molecule. Do you get it? Like atomization of chlorine is from the element you make 1 mole of gaseous atom. Therefore, since it's 1 mole, we put half here. Atomization of sodium is you make 1 mole of sodium atom, gaseous atom, from the element of sodium is solid. Like that. That's atomization, right? So do you remember electron affinity? -1. Electron affinity 2 is minus, getting -2, right? Then do you remember formation enthalpy? That's when you make 1 mole of a compound from the elements, right? Now this is the method. Now some data is not given. Some data is not provided. So we actually need data booklet today. But I will give the data whenever it's required, right? Okay, now this is the thing. So sodium oxide, Born-Haber cycle, we are going to draw. So remember Born-Haber cycle, when you are drawing, now you have a big space here. You need little bit of space to calculate, and you need little bit of space above. You start from the bottom, that's why, right? So we are starting from the bottom. So first I write down, don't copy anything. I'll give time, right? Just look at how I do it. So when they give, okay, they ask, find out lattice energy of sodium oxide using this Born-Haber cycle. First of all, I write down, okay, sodium oxide. Draw line, because this axis is energy, different energy are there, right? So sodium oxide, I write down. Solid. Now there are two ways of making this sodium oxide. One is from the element. So how do you make from element? So you take sodium solid. What's the element of oxygen? How do you write formula? O2. You get it? The non-metal is the gas. Metal is solid metal. O2. But balance it now. Is it balanced? No. 1 mole of a compound formed from its elements, we need to put 2 there. Half O2. Right? Then, when you make a certain compound from its elements, we call it formation enthalpy. Look at this carefully. Watch it like a small movie. Then you can do all these Born-Haber cycles, right? So you put formation enthalpy. That's formation enthalpy. And then you can make this ionic solid from its gaseous ions as well, right? So I will write down the gaseous ions, like, what are the gaseous ions I need? Can you tell me? Na plus and O2 minus. So I draw a line. I put gaseous ions and O2 minus. And I always check whether the equation is balanced. Not balanced. What should I do? Now, when you make an ionic compound from its gaseous sign, you call it lattice energy. First, we construct that. Now, this is the target. So I have target. Now, I want to go from here to here, which means sodium solid. I want to make it sodium gaseous ion. I want to make this oxygen molecules into gaseous 2 minus. So it's a big process, right? So first, I will always take the metal. Right? I take one by one. I don't like, when I work, I don't do everything together. Finish one and then finish the other one, like that. So I focus on sodium, then I'll focus on oxygen. So first of all, I realize sodium is solid. So to make gaseous ion, first of all, we need to make sodium gaseous atoms. But I didn't change oxygen, it's half O2. Right? So from solid to gaseous atom, we call it atomization. Delta H, atomization. Atomization, right? Now I have got the sodium gaseous ion, two of them. Remember to put two there. Now I want to make it sodium plus one. What is the process? What is the name? First ionization of sodium is required. So I make Na plus gaseous and oxygen. I haven't changed it. From here to here, put two, don't forget. That is known as first ionization of sodium. Get it? Now I'm done with sodium. Good, right? I'm done with sodium. Next is oxygen. Now, oxygen, I have molecules. First, I need to make atoms, atomization. But they will never give atomization of oxygen, atomization of chlorine, they won't give. What they give is this. Bond enthalpies you have to use from data booklet. Now see, if you break one oxygen molecule, how many atoms you get? Two. Now see if you understand this. To get one gaseous atom, but here we have only one, we need only one, right? Right? We need half molecule of gas, sodium gas. Now let's say bond enthalpy of oxygen double bond is 200. Grade 1 mathematics.
So
200, right? That is to make, oh, sorry, they can't see it. If I move to that side, no? Can't see, no? Now we all can see, right?
yes, sir.
It's perfect now. Yeah, now I can draw that and this. Yeah. Now see, if I'm using bond enthalpy, right? If I use 200, that's wrong because I'm getting two gaseous atoms, right? Because in this process, I need, like, I haven't changed sodium. It's there. I already made it to Na plus gaseous ion. So I'm going to make oxygen gaseous atom first. I need just one atom because it's one there, right? My point is, here to here, if you are using bond enthalpy of oxygen, if you use bond enthalpy of oxygen, that's wrong. Because you during bond enthalpy, you are breaking this bond and you are getting two gaseous atoms, right? So what should I do then? If I want just one gaseous atom, this bond energy, what should I do? 100. So whenever, if you are getting only one gaseous atom, the bond energy should be divided by 2. If you are getting two gaseous atoms, you don't have to divide, right? So therefore, so this is 100. So that means the bond energy of oxygen double bond should be divided by 2. This is something that always students forget. Remember the things I've told you all. Atomization of oxygen won't be given in the exam. Atomization of fluorine won't be given. Atomization of chlorine won't be given. Nitrogen won't be given because bond enthalpies we can use instead of atomization. So examiner will never give us atomization of oxygen, chlorine, or like those non-metals, right? Therefore, always bond enthalpy should be used. But when you use bond enthalpies, if you are getting only one gaseous atom, divide the bond enthalpy by 2. Because when you break a bond, you get 2 atoms. But here, if there's 2 atoms, you don't divide. Get it? Right. Then, okay, we are now reaching our target. Now we have to put an electron to oxygen. First electron affinity of oxygen, is it minus or plus? You can check the data they have given. It's minus. So the arrow should go down for first affinity. Do you get it? Arrow should go down. Right. Arrow should go down. I draw this level. Na plus gas. The board is shaking. Will it pause on me? Right. Okay, I'm gonna put one electron. It's -1 now. No, you have to do this. Bond cycle. Right. Now this is known as electron affinity 1. Then next step is getting 2 minus from 1 minus. That is electron affinity 2. Is it plus or minus? Plus, right? So that's why I did this like bit below this one, because the arrow should again go up. That's electron affinity. Electron affinity 2. Now see, now right, everything is perfect now, right? So after drawing the full Born-Haber cycle, now before I show you all the calculation, this is what you all need to understand, right? So what did I do? Revise quickly. What did I do? First, I drew lines like this and draw down the ionic solid. There are two methods of making the ionic solid. One is from the elements, the other one is from gaseous ions. So I put the elements, balance the equation. I put the gaseous ions, balance the equation. Then my target was to go from here to there. So first I took sodium solid. I made it a gaseous atom, two of them. Then first ionization, so I'm done with sodium. Then I took oxygen, made one atom, so that's bond enthalpy divided by 2. So after that, what did I do? So after you get oxygen atoms, you need to put electrons. First one and the second one. First one was exothermic, second one was endothermic. So the arrow goes up. So we have lattice energy now. Everything is connected in this diagram, right? So now you all can quickly write down. But when you write down, start like I did. First, I'll number what I did. Right? So first one was this. Second one was the lattice energy. I completed this. Then I connect from here, third, fourth. Then fifth was this, sixth, seventh. Quickly. Now breaks today. We'll finish this. Yeah. I'm also tired. I have a practical class after. Now there's no time to take a break also. 30 minutes left. So within 30 minutes, you have to finish 3 Born-Haber cycles. Yeah. No, if you do it fast, I will give you a break. So that's fine. You have some hope. So if something like, I missed something here, there should be 2. Always check those. If we had like chloride here, then you don't have to go to the second electron affinity. Then directly you're coming towards this, right? Only in oxide ion we had this issue. And 2, because we are making 2 atoms. Ionization should be multiplied by 2 because you are making 2 ions. That, the number of moles are important. When you make 2 atoms, you multiply atomization by 2. So mostly in exam we get a Born-Haber cycle. So if you learn the method of doing it, you can get full marks. Yeah. So, no, whenever you break oxygen double bond, you get two atoms. You get 2 moles of oxygen atom. So if you need 1 mole, 3, yeah, 1.5. Completed. Now we're going to use the values. Okay. So the calculation. Right. Now these are the data. Some data is provided, some data is not provided. But right. Now this is the first thing. Right. Now see if you understand this. Now to reach to this molecule compound, we have one pathway from elements, and the other pathway, like Hess cycle, this everything when you combine goes to our destination, another path. You get it, right? So if you add all of these here like that, you reach the ionic solid, right? So all of these are equal to formation enthalpy of lattice, sodium oxide. So, right, so which means formation enthalpy is equal to 2 times atomization plus 2 times the ionization, first ionization, plus half bond energy of oxygen plus electron affinity 1, electron affinity 2. But always take how many moles are there here, only 1 mole, so you do not multiply. So electron affinity 1, electron affinity 2. Plus, there's one more, lattice energy. Get it? So if you add all of them, you get formation enthalpy. Right. From these data, what we will never get is like ionization energy. You won't get it. because it's there in the data booklet. You have to find it from the data booklet, right? Bond energies, no, they won't give it because we can find it from data booklet. Others, they will give it because they are not in the data booklet. Electron affinity is not there. So now we're going to apply those values. So let's write down the equation. Then we know all of them. Like they will give formation enthalpy. They have given it in the table. Atomization is given. Ionization you can find from data booklet. Bond energy you can find from data booklet. So these two are given, but you have to find lattice energy. Sodium's ionization energy is 108 positive. It's anyway endothermic ionization. 108. That's atomization. Sorry, it's given. No? Ionization is not that. 108 is atomization. Ionization is 494. 490 plus 494. And what else we need? Bond energy of oxygen is 496. 496. That's also plus. Now can you find? First of all, put all the write all the numbers here, then solve and give me the final answer. Sorry? Minus 2500, yes, kilojoule per mole. And if there's a, you have to put the sign because it's enthalpy, negative or positive, you have to put it. It's definitely lattice energy is negative. So you have to put kilojoule per mole. Oh. What's this? Now you can start from the first one. Today we have to. Those who have finished, you can start from Roman number 1. So you finish Roman number 1, you finish Roman number 2. So before we stop, you have to finish up to page number 9. Huh? You have 1, 2, 3, 4 more questions. That's it. Very small amount of them. 4 questions. No. Yeah. How many we have today? 3, 5, 6. Finished? 6:30. It's a Radhagiri. I have to leave here sharp at 5. Half an hour? No. Did you all finish the calculation? Guys, hope you all can hear me. Also, for the further calculation, I'm going to send you all a PDF for those who have joined online. You can download it now, and then for you all, I'm getting a printout. So in that, all the energy data is there, like, the required pages are there from data booklet. Right. Previous question, what's the answer? Minus, right, correct, minus 2,523.2. Those who have joined online can check your answers well. You can see that formation enthalpy is given. Atomization is 108, so but it has to be multiplied by 2. Ionization is 494, it has to be multiplied by 2. Bond energy is 496 divided by 2. Electron affinity 1 and 2, you don't have to multiply, it's just same value we have used, minus 2,523.2. So let's start from Roman number 1, then Roman number 2, then there are 2 parts of questions, then only you can leave. My assistant is there until you all finish, even though I'm leaving. Yeah. Huh? Torturing? No. This is not torturing. This is tutoring. because you got 96, I'm disappointed.
So where have you sent the tube?
Yeah, what was the doubt? Snake.
Where have you sent the tube?
Sorry?
The PDF.
I can't hear.
The PDF, sir.
I just send it in the chat. You don't see?
So can you send it in WhatsApp?
Oh, yeah, I can. Chlorine bond energy. Give me one. Shall I first send them the? So y'all, what y'all can do is draw the Bonhammer cycle, write down the equation, and go to the next Bonhammer cycle. Then I can, once I bring the data sheet, you can quickly substitute the values. You can download from the group also. So there are 4 questions you have to quickly finish. It's like I'm giving a break here. I'm going to get the topics.
That's it. There's just like 4 people, 4 students. That me, honestly, why do they have so much better? Like, one is I want break. You also have to catch up from different stories. Anyway, it's from here. Honestly, I want to come. I'm a bit lazy. Into 2. I was planning not to come because I was thought like, okay, it's very stupid. So I just came and then what to go do? I say it like a potato. So I just looked at it. I wouldn't be bad. Sister, I don't come because waiting for me. Actually. I had to come with something OJ. I can't come. We have an October 6th day. Mama is so I said you were there. You tell me. I'll be like, I just come. No, I haven't been Sure. No, it has a long time. Don't come for this. If you don't come, you get I've been suffering so long without me for months. Facebook.
Sorry, on time. How many? Three? Okay, three. That's not. Quickly do.
How many of finish the first one? Yeah. Anyone from online? If you have finished the first one, you can send me in WhatsApp. Right. Shall we take the first one? Did you finish? This one? First part is this, right? So you put, right, you put a sodium, right? So the ionic solid is NaCl. So you can make it from elements, sodium and chlorine, but half chlorine because it's just one chlorine atom. And you can make it from ions, Na plus, Cl minus. So you have to start making sodium ion first. So atomization, you get gaseous atoms. Then first ionization, you get the gaseous ion. So you have completed sodium, then you have to move to chlorine. But chlorine at one atom we need. So the bond energy divided by 2. Whenever you need one atom, bond energy divided by 2. Because they won't give atomization of chlorine. Then after getting chlorine gaseous atom, you just need one minus. Minus 1. Electron affinity of chlorine is not positive. It's just negative, right? So the arrow is going down, you can see. So you get minus 1. Now everything is connected. This all, if you combine, is equal to formation enthalpy. Then in your equation, it's atomization of sodium plus ionization of sodium, ionization, first ionization. Chlorine-chlorine bond enthalpy divided by 2. Electron affinity of chlorine plus lattice energy is equal to formation. So then using all the data provided, we can find the lattice energy of NaCl minus 785. How many of you all got that? Right, now the rest you're going to do as homework, complete up to this page. No? Complete up to this page. Huh? Without completing, we are going to, if you have not completed, we're going to send you home. Come. Complete and bring it. Get it? Yeah. You have already finished everything? Oh, good job. Right, others finish and come, we'll discuss. Right, is it clear the lesson? Yeah, you just have to do everything by yourself and bring it. We'll check in the next day. Okay, guys, have a good day. Bye-bye.